Now let's look at the next example for this topic. This is the 0-1 knapsack. So knapsack problem is a classical optimization problem. And in 0-1 knapsack, you are given a bunch of items, and for each item you can either take it or leave it. And you want to put them in a knapsack that has a total weight limit. And your goal is to find a set of items that you maximize the value you take. So every item has a weight and the value. You want to take from the subset of all the items so that their total weight is below your threshold and the total value is maximized. And there are many ways of solving this kind of problem depending on how the parameters are. There are different ways to solve it. In this problem, we use the brute force fashion. So we simply enumerate through all the subset of items and then check every one. So this is not the best way to do it, but we use it to illustrate bit patterns, bit masks. So the sample code is provided. I guess I need to move the code to be under the C part, but the sample code is incomplete, so you need to get the add the code for generating output. So n is up to 20, so enumerating through all subset that takes 2 to the 20 subset, so that's doable. And the weight limit is up to 10 to the 9, and each of the weight and value up to 10 to the 9. So then what this means is when we add them up, then we could overflow int. So if we added the weight of any subset, we could overflow int. So we need to use a long when we add things up, even though each of these value itself will not overflow int. And the output, we want to store all the subset that achieve the maximum value. So we need to print out the maximum value and also the number of ways to achieve them. And then we output all the subsets that achieve that, the subset of items. And when there are multiple solutions, they should be output in the order based on the total weight. So let's look at these examples. We have 4 items. These are the weight and the value. Our knapsack can contain weight up to 17. So if we pick the first one with 11, then we can only include the last one. So that gives us a total weight of 124. But if we pick the middle two, we get a total weight of 128, which is better. So when we have a fractional knapsack problem, that is, we don't have to pick an item as a whole. We can take any fraction of it. Then this knapsack problem can be solved by a greedy algorithm. Essentially, we try to take as much of the item that give the highest sort of value per unit weight. So in that case, we will pick the first one. The first one, each weight has a 9 value, and the second and third, they all have 8. But when we do 0-1, then this greedy approach may not work, because by taking this makes it unable to take any of the second or the third item. We have to take the fourth, which is not very. Again, the unit weight is lower, and drag the whole unit weight of the set we take down. So let's look at another sample. So this is a 5 item for a weight of 10. So then this has there are 2 ways to achieve the maximum, which is 23. We can take the item 2, 3, 4 for a weight of 9. That gives us 3 plus 10 plus 2, 23. Or we can take item 3, 4, 5 that give a weight of 10 and also a value of 23. And we require to print the set with the lower weight first, and it's guaranteed that no 2 set that maximize the value have the same number of total weight. So this is just to make it easy for you to generate the output. So now Yeah, so then some of these test cases are with big numbers to make sure that you don't run into overflow issue when you submit. So let's look at the solution code here. So in this solution, I included a bunch of macros that I commonly use when I do CP. So in fact, let me actually turn the Wi-Fi as well. So in fact, these are fairly common macros used in the context of competitive programming. So it's used by many competitive programmers. You just make a code a little bit more succinct, so it's faster to type, and also just the meaning of code is it still remain very clear. Okay, so we read in the number of items and the capacity, and then we read in the weight and the values. So here we use this macro to repeat I goes from 0 to n, and so we need to store the best value start by initialize to be 0. So here I use a long. So this I define long to be LL because it's used use this multiple times, and I will store the solution in a vector of pairs. The reason is the solution need to be sorted in the end based on their weight. So then I store them as a weight and also the set bit mask. So actually, this shouldn't be indexed. This is a set bit mask here. Okay, so then the next part we enumerate through all the subsets. So S goes from 0 to 2 to the n, and for each S, I will compute its weight sum and the value sum. So this loop computes the weight sum and the value sum. It's similar to the problem we've seen before, subset problem we've seen before. And if the weight sum is no more than capacity, then this set can be contained in the knapsack. And we check its value. If it's greater than the current best, then this is a new best value. Then we don't need our remember solution anymore. We clear that and store this value. And then we add this solution into here. So we create a pair of the weight sum and the set bit mask, and then we make it, and then we push that into the vector. So after that we sort, and after that we output the best V and also the size of so here all and SD are macros. So all is defined here. It's essentially when I have all this is replaced by begin of this and end of this, and that's equivalent to answer dot begin parentheses and answer dot end. I can use the begin end as well. And SD is a macro for getting the size and then cast that to the int type. If we don't do that, we get this annoying warnings because the size is of this unsigned int type, because the size can never be negative, so it's an unsigned type. But a lot of the other variables we use are signed integers, so we get these annoying warnings even though the program runs. So by converting this avoid that those problems. Okay, then this is another macro. So we are traversing through all element in answer, and then we use P to be instantiated with each value in answer. So this is defined here. So we do a for loop where this variable and traversing over X, and we use auto type and this reference to avoid copying the items in the vector. So for each of the stored solution, the first P dot first is the weight sum. We don't need that anymore. We're not outputting the weight. We just output what is the subset. So that's P dot second. So here, the next part of the code need to generate the output. So if we run the code now, everything will be incorrect because we're not producing the set that's expected, and also we actually didn't use the s yet, so we get that warning as well. So then what we need to do is so this is a bit mask. So we have n items. So we want to check whether I is included. So then that is s bit mask bit end with we check the ith bit. So if this is non-zero, then that means this is included. So we should print this item. And after this one solution is done, we need to print a new line so that okay. So let's run it. Okay, so okay, so yeah, so I had a mistake because here I'm outputting 1 and 2, but they are expecting 2 and 3. That's because the item number is start from 1. So the problem interpret this as 1, 2, 3, 4. But here our index starts at 0. So we need to add 1 in order to get the correct element. Okay, so now it's correct. Now let's submit it. Okay. So